to this second presentation in this session.
Today I'm going to present
This session is entitled
Automated Quality Tracking for Surface Finishing and Construction. I'm a PhD student advised by
the presenter of this session is Mr. Juan Carlos Cruz Rivera. So he co-authored this study.
So in recent years, we have
a colleague of mine,
drone applications in construction.
So
So first, if the drone is equipped with camera and LiDAR, it can capture high quality environmental data. And if equipped with FDS and IMU, it can do programmable autonomous navigation and control.
Design and development of a remote
and
user
also it can do agile movement and access to confined spaces.
So
for example, they can work in narrow spaces and do vertical and angular movement.
This presentation
and because of that, the drone market rapidly rising in the construction with a compound annual growth rate of about 40%.
So it's going to be for
and the applications have now been expanded to visual inspection and monitoring. About 8% of the drones are now being used in monitoring and quality control works. However, there are still some challenges faced by drone applications in construction if you want to use them for some certain task.
For example, the introduction, my name is Juan Carlos Cruz, and I'll be presenting over here. So in recent years, there's been a growing trend for the off-site construction. So in our research project, we're particularly looking at precast components that are manufactured off-site and brought on-site to complete a structured construction.
However, these
typically on the off-site construction of these,
some vibrations,
inspections and quality inspections and things of the sort is very thorough. However, when you get on site, it becomes much more difficult because of different operating environment and different access to sensor and sensing equipment.
And also,
so typically, a manual on-site inspection
is rise of neural networks in drone-based visual inspection works. For example, we
saw opportunity there for automated inspection, that is bringing in research, robotic research into the space to perform higher quality inspection on site.
And we also have
and there's been a lot of background and related work to this. So drones have become very popular in both industry and research for this type of application in both structural and health monitoring.
And also enables zero-shot segmentation
and surveillance of construction sites. There's been a lot of work.
The knowledge gap here is that the existing drone-based
in terms of operating times and being able to
maintain accurate defect detection under motion induced image degradation. Also, traditional methods fail to handle motion blur, distantly, and variations in lighting and texture without
operating conditions
training
to perform.
And so our objective here is to develop a vision-based inspection framework
fully autonomous, but the technology is not really there yet. There's a lot of complications when you're working on different
under
environments.
Motion.
So because of that, most frameworks have a condition. That is a human.
So first, we have a LiDAR-based surface elevation module. The drone will use a 2D LiDAR to scan the ground surface and generate point cloud. And to improve accuracy, we first apply a signal noise removal filter to reduce errors, and then we perform a smooth interpolation to fill in the gap and generate a continuous surface model. So
most research starts from the ground up in terms of software.
And area,
so we want to provide some framework there and see what it could be applied
and consistency. Next, we move to the camera-based surface defect detection module.
So, as I described,
here we first use a convolutional neural network that can move motion blurs for us caused by the drone movement and reconstruct a relatively clear image of the surface. Then this deblurred image is fed into a vision transformer-based network, which can apply a multi-head self-attention mechanism to analyze spatial relationships and segment regions with potential surface defects.
This is facilitated through
together, these two modules
so for the drone, we have aerial controllers that the operator would use. And then we also have
high-resolution inspection for both elevation accuracy and surface quality.
Data streaming through the ground robot and coordination between.
So let's move on to our experiment part.
And
so
it's also open source. So at the end of the slide, then
to do assisted concrete finishing task.
This is a block diagram of system design.
In this task,
So as I said, we
this
have
drone should
ground
finish
robots.
the
It could
concrete
potentially be a
into
fleet of ground robots or drone.
And
what we have
so
though
during this
is
process,
going back to the previous
you see
slide.
the drone
So when we go
is
to the
equipped
drone
with the rotary
capabilities,
payload,
we initially
so
want to
it
get
will
some
have some
waypoints
vibrations
where the
because the payload is
object to be
contact with
inspected
the
is in
surface,
the
and we
construction site.
also
Because our
added a
initial
few
map might not
wind
match
disturbance to the drone
current state,
system
because
to
things tend to get
analyze
moved around and things go
to
slower.
add some
So we want to
extra
create
disturbance to the
waypoints,
system.
GPS-based waypoints.
So we also
mission,
collected
that have multiple
about 1,000
waypoints.
real-life motion
And
blurred
with the drone, we
images
also want to
for
get the
surface
contextual
detection
information. So the
to
ground
test
robot can then
the
do the autonomous
robustness of our
navigation
system.
to the location.
And here
that
it
contextual
shows
information in our case is
some
the target
example result here.
reference images. So that is
So,
images of the object to be
It
inspected.
shows the performance
so the
for
ground
our
robot has
advanced
some
drone perception system
later
here.
through a
To
computer
just
vision
recap
pipeline or
our
things of that sort.
objective here is to
So
develop
as
a
you can see here is
inspection
Streamline
framework
the
that
user interface app
integrates
where the
multimodal
operator can
inputs
coordinate the
for
data flow.
accurate real-time
You
defect
have the gaze
detection.
module, as I discussed.
So
And
we can
we have
see
another
left
little
is
module there at the
real
bottom. It's a
blurred image,
segmentation
and
module. So with the gaze
then after
data,
we
we get
blurred the
pixel
image, the
coordinated points.
segmentation results
So very
after
fine,
deblurring is much better.
low-level information.
And
And we want to
quantitatively,
expand that
without this
and add
deblurring, the
in order to get a larger grain of
0.78,
information
but the
of
recoil
what
is
needs
just
to be inspected.
0.15,
So with a single
and the mean IOU is
say,
0.28, and
you can get a
the
larger
task
map
completion
of
rate, which
what the
means
robot should be
the
inspecting.
surface finishing task, is only 10%.
And this,
However, with our
additional system
deblurring
design, we use a containerized
module,
architecture.
the
So
precision
containers such as
recall
Docker
can go up
containers
to
that we
about
use in this work
0.55, and now the
can be
mean IOU is
coordinated through a
also
Docker compose,
95%,
which
and
allows
the
you
task
to
completion
coordinate
rate is
multiple
now
containers into a
90%.
larger application. So containers are usually
In
isolated.
conclusion,
That is, they're
the major
isolated
achievement
virtual environments or virtual machines,
this work is
but
determined by
are
the
much lower
motion
level,
blur
so they have
removal
kernel level access,
module, which
and
can
are
successfully remove
ideally
motion blur
they
from
can be
from
replicated
captured
on the
images,
So
improving
through a
segmentation
configuration file,
performance,
you can spin up
and
this environment
raising the
and have a whole application
IOU
deployed.
from
very
28%
quickly.
to over 95%.
So
And also
we
we
manage
have
the
an
communication
integrated
data flow
perception
between these different
system
isolated
for
environments,
surface quality monitoring,
using the
which
zero
enabled defect detection without extensive
data
labeled
library
in
and
data,
proxies between them.
and improving the adaptability to new safe
And this
surface
is a
textures
image of
and
the user
interaction
interface.
conditions.
The user interface for the ground
There
robot
are also
is
some
aerial
future
streaming.
directions.
So one of the benefits of this is we use a
currently the
browser-based application.
computational demands for
So
learn-based
that allows us to
perception
deploy on
module
multiple
may
operating
bring
systems,
challenges
browser
with limited computational
as
resource
you
on
can
board.
see here, we have buttons for
And
the
still
state
the
indicators
experiment is
for
still
where the robot is within the
simulated
mission pipeline,
or controlled
which we'll see in the
environment,
next
which
slide.
means we
And
need
we
to
also have some
explore
April tags.
more
So as
real-life
we've said,
behaviors in future.
the operator has gaze interface. So these April tags allow
At
us
the
to
end, I would like to extend
create a
my
bounded
gratitude
area
to my
in which the
advisor,
gaze
lab
is
mates, and all
used.
funding resources.
So
for
that allows us
their
to get very precise pixel level.
Thanks for listening. That's
Pixel level location of where the user is looking and where it's fixing.
Yeah, thanks so much. And suppose we have enough time for discussion.
So
We welcome any question or comments from the audience.
We have a drone cage of the
Any
UTSA
question?
that allows us free range and free roaming within this space. So we tested with a mock environment. You see a bridge there we put
Now,
into
let
the
me start
environment
with my
using
question.
a local Wi-Fi.
As far as I understand, the key point is that the payload is not static and it's moving. It's working on the surface, right? So the first question is the machine. Something like the machine, it's firmly coupled with the drone itself. Or it's just suspended from the drone by wire or flex.
We have 3 stages. The data gathering stage, as I said, this one is where the human operator would send a drone to a location. So if you were going to inspect that bridge in the previous picture, you would send the drone there first. Gather GPS-based waypoints. And
I suppose you mentioned the computational.
And then if you have multiple, you can.
I mean, the program will
once you have
computation
those,
in the future work. And did you confront any difficulty coming from
those
the
then get
computation
sent to the mission
at
execution
this moment?
in which the ground robot or fleet of ground robots would coordinate to dispatch to those locations. Once they autonomously drive to those locations and find the area of interest, then you would have the inspection phase, and this is where the gaze-based portion comes in. in order to get more fine-tuned data and also specify what exactly we want to inspect within this
battery system,
component.
and the cable can help us to transfer the.
And as you can see here, this is the deployment phase of it. So the orange area there is the segmentation mask that we create. The red point, if you can see it, is the fixation point. So once the user fixates on the target, we then segment that area, and the ground robot would then know to
current experiment you conducted
intelligently navigate to that area and perform a surface level inspection or whatever kind of inspection would be needed.
Okay.